All right, let's talk excitation methods or techniques today. Anybody who's doing any kind of vibration analysis, modal analysis, is going to get into this question sooner or later. So I want to start with, before I show the different methods I want to talk about briefly, these are some of the questions you want to ask yourself as you select or are in the process of selecting the excitation method. How much force, frequency range, the size of your structure, test duration, all this. So I don't want to go through this, but as you ask these questions to yourself, it'll point your sort of guide you, it'll filter out the method that will work best for your application. So getting to the summary, this is what I wanted to show you today is, broadly speaking, I'm sure there are more, but contact and non-contact excitations. I picked a few that are more popular, widely used type methods. So let's go through the contact methods, the piezo, the hammer, the shaker first. We should start with the hammer, one of the oldest methods of excitation since the beginning of modal analysis, and started off with a manual hammer. And to address some of the drawbacks of the manual hammer, with the double hits or, the repeatability not being so good, were addressed using an automated hammer, which is what you're seeing on the bottom here. So definitely consider the automated, especially for scanning vibrometer measurements where you can have, several hundred or thousands of points with more than one averages. So you're talking a lot of good hits. So that's where an automated modal hammer would be very helpful. The specs are up to 20 kilohertz, but there are some measurements with smaller hammers that go all the way to 40 kilohertz with a modal hammer. So that's the quick one on the hammers. Another very popular and widely used is a modal shaker, electrodynamic shaker. This is good when you need continuous excitation. So that's so periodic chirp or white noise, burst random, those kinds of excitations. The shaker is connected from the base to the structure using a stinger. The main function of the stinger is to ensure that the excitation is unidirectional in the direction of interest. Usually both the modal hammer and the shaker also use either a force sensor or an accelerometer to measure the input energy, the energy being input, or also an impedance head that has both an accelerometer and a load cell. So that's a quick one on the shaker. Another one that's up and coming, definitely currently used more for higher frequency excitations, is the piezo-based excitation. And generally, it goes with an amplifier as well to protect, for the impedance matching and protecting your electronics. But certainly something to consider. I have a couple of examples to show you here. On the right is a piezo disc being used to excite a brake rotor. And on the left is a composite panel. In this case, we are using a piezo stack. And again, good for continuous excitation, high frequencies that kind of go beyond what the modal hammer or a shaker can handle. The one drawback that, for traditional modal, you want that force input or energy input, and those are kind of, you need a, have a special type of piezo to do it. It's not inherently measuring the force input as well. So something to keep in mind if you consider the piezo excitation. So that covers the contact side of things. With the non-contact, let's start with the acoustic excitation. Very easy to use. A speaker, or a focused acoustic source like a parametric speaker or an acoustic horn would be good examples. The only thing, something to keep in mind is the efficiency would not be comparable to a mechanical excitation where you are in contact with structure, but very easy to use. And in many cases, the only way to do it, and that's what I have down below, a couple of examples. We do measurements on tympanic membrane for ear mechanics. So this would be a good case for an acoustic excitation where we use a little speaker to excite the eardrum or the tympanic membrane. On the left is a tiny turbine blade. Again, if you mount something on it, you're going to affect the dynamics. So we are using an acoustic horn in this case. So both are good examples for using acoustic excitation. So that covers that. Now let's go to one more. This is laser-based excitation. Again, very a little niche method to do the non-contact excitation, but could be very helpful, especially some of the high frequency applications or where you want to speed up things would be a good one to consider. This study here is by researchers who were doing some defect detection. In this case, instead of rowing the sensor to do a scanning measurement, they were rowing the excitation using a mirror set, and then moving the excitation and then coming up with a full field response of the measurement. So this is a good sort of case study for a laser-based excitation. And finally, no excitation. So these are a couple of examples where you're not artificially or externally exciting it. It's just the inherent nature of the structure that is exciting it. So think of an engine running, or a run-up measurement would be a good case, or dwelling at a certain engine speed. In terms of wind turbine blade measurements, the wind exciting the structure itself would be a good case. AFM tips, Brownian motion, thermal excitation. This also shows the ability of the vibrometer to measure very, very, very small amplitudes of measurements. So that's a good summary of where we are as far as different excitations. And again, going back to the summary, hope that gets you going somewhere, at least something. So reach out to us if you have any questions. Until next time, see you later.